Good. So we were able to connect. I don't know why it's so shadowed, but in any event, it is visible. So my aim is now to repeat the proof of the previous theorem about point-wise convergence. And I will be very quickly. So I will be very quickly just to record and repeat the main steps So the class of functions where we prove everything. Point-wise continuous. Yeah. So the function is pieces of continuous function. Somewhere jumps, but we always want that limit from left-hand side exists and limit from right-hand side exists. So this is the space which we call E, Then we also want, of course, it would be good if function has derivative, but if function is piecewise continuous, it maybe has no derivative. Therefore, we introduce right-hand derivative and the left-hand derivative. Usual derivative, but we approaching only from one side and another side. The best example is absolute value. So if you go from this side, we will get derivative 1. If you go from this side, we will get derivative -1. So this is the main space E prime, where we want to prove convergence of Fourier series. Of course, not to the value of function in the point, because function has, in some places, it's discontinuous, so it could not converge to the value in the point. A very good remark that if function is differentiable, it belongs to this space. Moreover, if function is piecewise continuous, we can integrate its square at each piece. So any function is in L2. So now we study this convergence in some subspace of L2 space. So L2 space is larger, but this E prime is its subspace. So we know that in L2 space, there is convergence of integral, square of integral. In this space, which is smaller, in this space E prime, we hope to get stronger convergence point-wise. Last lecture, we studied how they are related, these convergences, yeah? So we know that from convergence here, we don't have convergence here. So before we proved convergence of Fourier series in L2, but it does not imply point-wise convergence. We gave example of this movie when the areas moved to 0, but the spikes were going in different directions. So now we consider it in this space, subspace E prime. Convergence here is does not imply convergence point-wise. So now for functions from this space, we want to prove convergence point-wise. So this is our aim. And formulation of this, I think, the main theorem of the theory of Fourier series. So for each function, we write Fourier series. So these are coefficients given by integrals. And if our function belongs to E prime, then the series converge point-wise to this average of x limit from right-hand side plus limit from left-hand side divided by 2. This means that for any x in the segment, partial sums until n large of this series converge to this number. If function is continuous, all this business has no meaning, it is just value of function. So if in some point continuous, then it is just represented by Fourier series. So if function is continuous, then it is just given by Fourier series. So in principle, you can consider continuous function which has continuous differentiable function. Or for continuous differentiable function, we are always sure that Fourier series converge to this function. So for example, if I ask you, for example, if I take function exponent x, does Fourier series converge to it? Yes, function is continuous and differentiable. But it's also converged to absolute value of x. So absolute value of x is also continuous, and it has left-hand side and right-hand side derivatives. So series converge in any point. Oh, good. So there's a slight difference. Existence of these limits and coincidence and existence of derivative. So here it's enough just existence of left-hand side derivative and right-hand side derivative. So for absolute, here we can write, for example, absolute value of x. It's given by Fourier series. So the proof is long, but it is not so I can say intelligent. So in this series, the main block is this. Let us represent this block by integral. So we put instead of ak, its representation as integral 1 over pi fx cosinus chi tx. Here, so we get some integral where is fx and the sum of cosinus kx and sinus kx. So we use the formula cosinus of the sum and so on. But now we want to get one integral. What is in this theorem is not written, but we discussed this. Each function should be periodic. Maybe they told this before, because otherwise it is not correct. Because as we see, Fourier series is a periodic function, who is E prime of all functions. No, it's the space of piecewise continuous functions. It seems that they never made restriction that it is periodic, but it should be this restriction. Okay, so in any event, we assume that function is periodic. Because periodicity is used already in the first proof. So we want to prove this formula. So as I told, we put just these integrals, then we collect them in one integral. How we do? So we put this. So finally, we collect, this is just trigonometry. This is equal to this cosinus. After this, we make the change of variable. T minus x is equal ks. So here is misprinted this book, Fourier analysis in the Hilbert space, which is on my model. Here should be plus, because we should have the length of interval is the same as here. We study the chief function is periodic. Then if you move it on this on the interval has the same period, integral is the same. So I think I'm not wrong. So this minus this should be equal to pi. So pi plus x minus plus pi minus x is 2 pi. So here should be plus. Small misprint. Now we have this integral, which is from this to this. Difference between these 2 points is period. And now we claim that it is equal to this integral over minus pi. So this is what was my remark. We consider this function of s, cosinus ks is periodic. This should be asked in the formulation of theorem. I should write maybe somewhere that function f is also periodic. So this function is periodic. Therefore, when we go, well, they wrote this in fact, that if you integrate over some interval where the difference between this and this is 2 pi, it is the same as from minus pi to pi. So when we move from this to this, we use periodicity of our function. Yeah, that's it. Nothing so complicated. So we approached this formula. And now we put it into our Fourier series, into partial sum. And we shall get such representation of partial sum of Fourier series. So there is this 1/2 and sum of all cosinuses. All cosinuses. This sum has its own name. It's called a Dirichlet kernel. Dirichlet was German. I don't remember. Maybe German, Dirichlet, German or French. All mathematics was done more or less in Italy, Germany, and France, and Great Britain. Yeah, so these 4 countries did basics of mathematics. Mainly Germany, France, and Italy. They were I had a course in the United States in California, and American students were a bit disappointed. They thought, why all names are of this European, but it was done long before science was developed in other places of the world. Okay, so this is Dirichlet kernel. And what it is claimed? It is claimed that now we can write our partial sum as integral with respect to Dirichlet kernel. So this is precisely Snx. So this integral, it's a partial sum of Fourier series. So now they claim, so this is not proved, what they claim. They say we'll prove that this integral go to what we want, So this is more or less formulation of our theorem. Moreover, this theorem is in fact has 2 blocks. The integral from 0 to pi, this part, is go to this, and integral from minus pi to 0 go to this. It's again question. So this is now the lemma. They want to calculate this Dirichlet kernel, which has this form. Lemma is very simple. We use just Euler formula for cosinus. The cosinus kt is this. So this is cosinus. Here is again misprint. So by some reason they wrote integral is sum. So this is the sum of this and the sum of this. Both are geometric progressions. And you know from school or somewhere the formula for finite sum of geometric progression. The proof is the same in complex numbers, in real. They exist even so-called periodic numbers. It would be the same. So, and they calculate this. And then they want to extract sinuses, yeah? And so this is sinus with minus, and then minus go up. And this one, and this is this one, and we see that here is plus. It's again already good for sinus, and here is minus. Here is plus, here is minus. So we did this calculations with geometric progression. And finally they collect everything. Here is again misprint. Here should be minus. When they subtract 1, they write the sum of these 2 guys. And again, the main misprint in this text, they put here I. Of course, there is no I. If it is this, it is just sinus. If it is this, it is just sinus. So everything correct without this I, which I destroyed. And again, the answer is this without I, which is again destroyed. So this is the formula. So this is the formula for Dirichlet kernel. No, nothing great intellectually, just geometric progression and Euler formula. Nothing more, no, some computations how to calculate the sum of n terms of geometric progression. No. They introduced 2, I think, supplementary functions. In principle, this is practically right-hand derivative and left-hand derivative. But since in Dirichlet series we have in denominator this sinus 1 t divided by 2, they put not just t put here in denominator, but sinus. So it should be t to get derivative. They put the sinus. But sinus practically t. If we expand this, and it is t divided by 2, so this is practically t. Now, Well, in reality, if you have the limit from the right-hand side, you can write in this way, more or less what I thought. So we get right-hand side derivative. So these are supplementary functions, which in fact produce right-hand and left-hand derivatives. They exist by formulation of theorem. In theorem, we ask if this exists and this exists. Okay. Now they told. Now we shall prove that in fact this limit is equal this. They just repeat it was on the previous page, and here somewhere misprint. It should be 1 over pi from minus pi to 0. This one. So, and if we prove this and this, we get this. So they more or less repeat what was on the previous page. Now they even formulate a special lemma. This go to this and this go to this. What it is used in the following lemma, that we want to represent this as integral. This is constant, and we multiply and divide it by pi divided by 2, and then we get Dirichlet kernel. So if we take this function, it is constant from integral of Dirichlet kernel is pi divided by 2, so it is just this one. So this is how to calculate this integral. I have not done last lecture. I shall do now. It's very strange because it does not go straightforwardly. For example, what I wanted to do at the beginning, who is Dirichlet sum? Dirichlet kernel. Dirichlet kernel is this one. So the one of ideas to integrate is to expand sinus as the sinus of sum of two angles, but this guy is very bad, and it is very long calculation if you go straightforwardly to calculate integral. Then I wanted to save time, and I went to YouTube, and there is video, 30 minutes. The guy struggled with this integral. Finally, he got pi divided by 2. But then I show you how to do this. After this video, I immediately understood that one should do something different. Yeah, so we go. Yeah, this we already passed. So we have all this will be done maybe in 5 minutes. Now we go here and we wrote this difference, which we want to prove that should go to 0 in this way. Here is Dirichlet kernel. So this constant is also written as integral. Yeah. Now we get this expression. And now they tell that we should use Riemann-Lebesgue lemma. And then this go to 0. Then this go to 0 when n go to infinity. So this is the end of the proof. So this is go to 0. And the same we do on the other block from minus pi to 0. So Riemann-Lebesgue lemma, which we get presented as kind of scheme how to prove it. So if function is absolutely integrable, so its integral is less than infinity, then integral this function by this exponent go to 0 when alpha go to infinity. So as I told, physically it means that when alpha go to infinity, this is cosinus alpha t and sinus alpha t, they flip to it very quickly. So they destroy our function. Where function is plus, immediately here they produce minus and function disappear. So this is not usual decreasing of integral because function can be sufficiently, function does not go to 0, and this does not go, neither go to 0, it's equal to 1. No, in particular, this integral, real part go to 0, and complex imaginary part go to 0. So we proved this very, very long theorem about pointwise convergence of Fourier series. Now we stop share. Stop share, and now we go back to our blackboard. We go to blackboard. Yeah, we don't need more projectors. Off. Yeah. So now we click blackboard. And we have few tasks. I shall move computer. We have few tasks which have not been completed. Oops. Why I don't see anything on camera does not work. Why camera does not work? No. But I don't see anything on. I don't see any. It's okay.
Yeah, it's fine.
It's fine. Yes, I just yeah. I just wanted to see that it would be something on the way, but it's not correct. So now go back to Dirichlet sum, and we want to calculate this integral, for example, from 0 to pi. It is sinus n plus 1 plus half t sinus t divided by 2 dt. In principle, I still do not know how to calculate this terrible integral, but let us remember who is this Dirichlet kernel, this guy, Dirichlet kernel. It is, in fact, was obtained from Fourier sum. So we got this by summation of this series. So we just go back to the very beginning. So this is Dirichlet sum. If you recall who is Dirichlet sum, it's very easy to integrate it. You don't need any tricky change of variable, anything. The first term gives us this p divided by 2, which we wanted. And the second term will give sinus, but sinus in 0 and pi is 0, so plus 0. So it's pi divided by 2. Yeah. So this is the last block of this theorem on point-wise convergence, which we should complete. Okay, now we go to this. This course has 3 parts. This course has 3 parts. 1, complex analysis. 2, Fourier series. 4 parts, I think. Yes. And the third part is the part from usual real analysis, different types of convergence. Types of convergence. Of course, it's related, but it's very different thing. Yeah. So, and then we have still after this we have 5 parts. 5 parts. I think it was Joachim Toft who was designer of this course, and my impression is that only he can pass exam for this course. Yes, so but we should simplify as possible, but in any event, it's very difficult course. So then we should study Fourier transform by itself, very delicate thing, and finally Laplace transform. So now this we finished, and now we on the third point. on this short point. After 4, 5 is more or less the same. So Laplace transform is very similar to Fourier transform, very similar. So, okay, go to types of convergence. What types we studied last lecture? First type, point-wise. Point-wise. So for any x, fnx go to fx. Second, L2 convergence. L2 convergence. So it means that integral from a, b, for example, if it's L2 on a, b, fnx minus fx square dx go to 0. As I told in application, this means that the energy of the difference of two signals goes to 0. So this is one signal. It is typically approximated by other signals, for example, by partial sum of Fourier series. And the difference of energy in this sum and our original signal go to 0. How they are related? By example, we show it, we demonstrated. A2 does not imply point-wise. More in our example, sequence of functions does not converge to f in any point, but the difference between them in integral goes to 0. Now we want to show that other way around. So point-wise does not imply L2. Does not imply L2. So it can be, this look more strange, that in each point there is convergence, but nevertheless, the energy, the difference between energies does not go to 0. Yeah, to find such example, we should be aware about one theorem. So, how to find such sequence which which converge point-wise, but not in L2. We should be aware about the following theorem from the. It's again a bit a problem that we did not have the course on integration theory. So this such theorem which constrained the how to construct example. This is from integration course. And this theorem tells us the following. So let fn x converge to fx for any x. So converge point-wise. But it's not enough to get let fnx all bounded by gx, where gx is integrable, where integral from a b gx dx is less than infinity. Of course, gx is non-negative because it's from boundary majorate absolute value. So it's called Lebesgue's theorem on majorate convergence, but it's not important for us for its name. Or we can write it. It's called Lebesgue theorem. Lebesgue was French, a mathematician who more or less created modern theory of integration. So when we want to construct something which is converged point-wise, but it is in particular remark. In particular, if they are just bounded, the constant is of course integrated. Then so if O f n x are less or equal than z, then I did not get what happened. I wrote that conditions of theorem, but what is then? Then we can change integral and limit. Limit and go to infinity. Integral dx is equal a from b limit fn x dx, and this is just integral from ab fx dx. So if the sequence of functions converge pointwise and majorated by integrable function, then we can change limit and integral. Then we can change limit and integral. Okay. So if you want to construct such point sequence which converge pointwise, but for integrals we don't have convergence, the sequence should be unbounded. So constraint that we are in the process to construct counterexample. We want to have example when sequence converge pointwise, but not in integration meaning. So it's clear that this sequence should be unbounded. For bounded sequences, does not work because if here is constant, so if O f n x less or equal than constant, then let us denote this block as star, then star holds. So if sequence of functions is bounded by some constant and converge pointwise, then we can change integral and limit. So if you want to construct counterexample, then it should be a sequence of unbounded functions. So now we are going to give such counterexample. So let us consider sequence. The idea would be also very simple. X, y, fx. Let us do the following. Let us consider some unbounded function. Yeah, 0 and 1. For example, function 1 over x. So it's clear that it is going up very quickly here, and area would be infinite. So we do the following: make here 1 over n, and here our function is here 0. We don't want to have infinity in the point 0. So our function is here 0, and here it is just this. So here it is 1 over x on this block until here, and here it is 0. So we can write in the following. This sequence is unbounded, so when n go to infinity, it's go to infinity. It is unbounded, what we wanted. So the Lebesgue theorem is not correct. So, and we define formally fnx equal 0 when x is on this interval 0, 1 over n, and 1 over x when x belong 1 over n, 1. So this is our sequence of functions. Pointwise, what happened with them? Fnx converge for any x, converge to fx which would be in 0, it is always 0. So it is would be 0 in the point 0. And if it's not 0, sooner or later this will come here and it will become 1 over x. So it's 1 over x, x not equal to 0. But here we cannot, here it cannot be, here this from 0 to 1, fn x minus fx square does not go to 0 and go to infinity. Because this function is not integrable, because integral from 0 to 1 is square 1 over x square dx is equal to infinity. So the limiting function even is not integrable. Square, no, not only square, but it's 1 over x neither integrable. Yeah. Okay, so we proved that pointwise does not imply L2. Does not imply L2. But of course, only in the class of unbounded functions. If function is the sequence of function is bounded and converge in any point, Lebesgue theorem tells us that we can change. If you write here, if it would be bounded, we can write limit here, then it's moved here, and then we will get 0, and then it will be 0. But we cannot change limit and integral, because Lebesgue theorem does not work for this sequence of functions. Okay, so we studied two types of convergence, pointwise and L2, and they are very different. There is no only Lebesgue theorem give us some connection. Yeah, so if sequence converge pointwise and bounded, then it's convergent L2. Then it's convergent L2. Okay, now we go to the third type of convergence. This convergence is very strongly used in the course of functional analysis. And now I'm really in great surprise, because students who typically come to me to the course of functional analysis, they had this course, but they have no idea about this convergence. No, it's happened. So the third type of convergence is uniform convergence. Uniform convergence. Uniform convergence. It is stronger than pointwise convergence. It is stronger than pointwise and even L2. So we denote this in this way, Fn and two lines. This is uniform, the symbol for uniform convergence. And if it's converged uniformly, it's implied pointwise and imply L2. So if we so lucky that for example, if we're lucky that Fourier series converge uniformly, then it's of course converge pointwise and even in L2. What is the definition of uniform convergence? What is the definition of uniform convergence? First, I recall you definition of usual convergence. Yeah, epsilon, for any epsilon, there exists such number depending on epsilon, which for any n larger or equal than n, we have such the difference fnx minus fx is less than epsilon. So, yes. This means that fnx converge to fx at the point x. The point x. What is important, and typically in your course of usual analysis, maybe even your teacher, epsilon, yeah, did not pay attention for this because there was no need for this. This number depends on x. For each x, there exists its own number when we have this inequality. So for one x, it can be 100, for another 1 million, and so on. The crucial point is that, and depends not only on epsilon, but also on x. For different points, fnx becomes very close, epsilon close to f, starting with different number. Uniform convergence is such that this number does not depend on x. So, convergence is called uniform if n epsilon can be selected independently on x, because n epsilon is not uniquely defined. We can take it larger, smaller. No? It can be selected independently of x. And now we give general definition через epsilon delta. Yeah, the definition. Let x. So now we need not be on a real line. We can be on any space. Let x be any set, and fn are functions from x to real line. And let we have the following: for any epsilon, there exists an epsilon not depending on x, such that I will go up, and I don't need maybe even write anything, because it would be, let us, you need to rewrite, let us denote this block by, for example, 2 stars. There exists epsilon z such that 2 stars holds. First of all, sequence of functions now can be on any set. We don't need to have it on real line. So this is any set. Values is still in real line. So this is definition of uniform convergence. There is for any epsilon, there exists number does not depend on x, and we have this for any x. We can rewrite 2 star. Since this is for any x, we can take here supremum. So we can write supremum of both sides, supremum of epsilon is epsilon, fnx minus fx, with respect to all x in x, and this should go to 0. Go to 0 and go to infinity. So pointwise convergence is just this go to 0. But if it is uniform, we take in this inequality supremum of this part and supremum of this part, it is still epsilon. So we get the supremum of difference with respect to all points is less than epsilon. So for uniform convergence is convergence of supremum uniformly with respect to all x in our domain of definition, and this supremum of difference should go to 0. Okay, let us make break, and after break we study the properties of uniform convergence, especially because it would be very much used in the course. Last lecture, I forgot to record the second part, and I talked to my colleagues about this. And one of them make jokes that now you can apply for the president of United States. Yeah, so this is so I'm not worse than Biden in any case, because I was very, very low after this. Oh, my brain is so bad, I forgot to start recording, but he told, no problem. So we have this, and it's clear that from this, if its supremum go to 0, in any point of course it go to 0. It is evident that Fn go to F imply F and x go to Fx for any x in x. So uniform convergence, of course, imply point-wise convergence. It's trivial. If supremum go to 0, of course, in any point it's also go to 0. Other way around is not correct. So we should construct example of sequence of functions which converge point-wise but not uniformly. Converge point-wise but not uniformly. Before we prove the following theorem about uniform convergence. Theorem. Now let x would be a segment of real line. So in real line, and let for any n Fn is continuous on real line, say AB, continuous on real lines, and Fn converge uniformly to F. So we have a sequence of continuous functions on segment AB, which uniformly converge to some function. And then this function is also continuous. Uniform limit of continuous functions is continuous. The uniform limit of continuous functions is continuous. Proof. First, we should recall what does it mean to be continuous in some point. Yeah. So, G is continuous at the point x0. What does it mean? For any epsilon, there exists delta such that when when points are very near to x0, this implies gx minus gx0 is less than epsilon. Before Cauchy started to terrorize mathematicians with epsilon and delta, the reasoning was if x is near x0, then gx is near gx0. Maybe a few hundred years they work in this verbal formulation. Okay, so now we know that any Fn is continuous. Any Fn is continuous, and okay, so we have that C uniformly converge to F. Uniformly converge to F. Take x0, and we would like to estimate Fx minus Fx0. X minus Fx0. What we do, we put here, we use triangle inequality, and we put here Fx minus Fnx plus Fn x. And here we also want minus Fn x0 and plus Fn x0 and minus Fx0. Oh, we put this. In fact, it's still equality. Still equal. We just subtracting it. So this block would be responsible for, would be based, it would be small because each Fn is continuous, x minus x0. And this would be around 0 because Fn converges to this, and this would be the same, yeah? So now we make this less or equal Fx minus Fnx plus this Fn x0 minus Fn. So this is analysis of function of one real variable. So this was very popular maybe 100 years ago. And plus this block, which would be responsible for continuity. Yeah. Now, since we have this, that they converge uniformly, for any epsilon, we can find such number that this would be less than epsilon for any n, and this would be less than epsilon for any n. So they exist such n epsilon that, no, let us denote them u1 plus e2 plus e3. So because of uniform convergence, there exist such epsilon that e1 is and here we put n, okay, less than epsilon, and e2 is less than epsilon. Yeah. So because of uniform convergence. Now take some n, this epsilon for any n larger or equal to n epsilon. Now take some such n and use that Fn is continuous. Use continuity of this function. Then for this concrete function and this concrete n, one of such that satisfy this inequality, because they satisfy this inequality, we already have this less than epsilon and this less than epsilon. Now we're struggling with the last term. Okay, so since function is continuous, for any epsilon, there exists delta. When x minus x0 less than delta, we have that this is less than epsilon, so e3 is less than epsilon. So now we can formalize this in this way that if we take for some epsilon such delta, which we selected for this function Fn, then the difference, our original difference, would be less or equal than 3 epsilon. So we proved that for any epsilon, there exists delta such that when x is so close to x0 as this, we have fx minus fx0 is less than epsilon. So function f is continuous in the point x0. Function f is continuous in the point x0. We use two things. First, this can approximate f uniformly in all points, because this point and this point. If convergence is not uniform, for each x, its own number, and then for each number its own delta, and we would never find the minimum of this delta would be 0 if it is not uniform convergence. But it's uniform convergence, it's 1n, and all for all x is less than 2 epsilon. It would be, no, we got 3 epsilon, that's 3 epsilon, but it does not play any role. 3 epsilon. No, from the very beginning, we can write here epsilon divided by 3, epsilon divided by 3, epsilon divided by 3. Yeah, so uniform limit of continuous functions is continuous. This is good result to construct very simple example of sequence of functions which converge pointwise but not uniformly. So we use this theorem. A sequence of functions converge pointwise but not uniformly. We will get sequence of functions converging pointwise which limit is not continuous. So this means that convergence is not uniform. So example is such: x, y, and from 0 to 1. So my segment is x is segment 0, 1. And function would be the following. Here it is 1 over n. Here it is 1. And here is straight line between these points. And here function is 0. So this is fn(x), which is equal 0 x belonging to 1 over n, 1, and straight line x belonging to 0 to 1 over n. And then in any point, if you have any point x, sooner or later, this will come and make function 0 in this point, because this straight line goes to 0. So for any x, there exists such number that fn(x) is equal to 0. For any x not equal to 0. And if you are in the point 0, all our functions are always 1. For x equals 0, fn(x) is equal to 1 for any n. For any n. So this means that pointwise, our sequence converge pointwise. Our sequence converge to pointwise fn converge to f, which equal 1 for x equals 0 and 0 for x not equal 0. This function is discontinuous, so convergence could not be uniform. Since f is not continuous, convergence is not uniform. Okay. So uniform convergence really stronger than pointwise. So the stronger than pointwise. Now we would like to understand what is the relation between uniform convergence and, for example, L2 convergence. Yeah. And we prove the following theorem. This is very good topic on the exam, and the exam, I more or less promise you it will be a question. Compare 3 different types of convergence and separate them by giving your own examples. No, you can use my examples, of course, but if you have your own, it is better. Yeah. So pointwise, the weakest, not the weakest, pointwise and L2, they are not. We cannot say what convergence is stronger. It's better to say uniform is the strongest and imply all others. From pointwise, we cannot get uniform neither L2. And now we want to prove that from uniform we get L2. Our aim is to show that uniform is really the strongest. So from uniform, we get not only pointwise, which is trivial, but even L2 convergence. Even L2 convergence. So theorem. Let Fn x be integrable functions. What is more? Fn uniformly converge to x. Then integral from a b Fn x minus fx, or we can write this way. And integral from a b Fn x dx minus integral from a b fx dx. This is less or equal integral a b Fn x minus fx dx, and this goes to 0 and goes to infinity. Here I use such inequality that you should use in the course of usual analysis. Integral from a b gx dx, absolute value less or equal integral of absolute value gx dx. This was somewhere in the course of usual mathematical analysis. Absolute value of integral is less or equal than integral of absolute value. Okay, now we prove this theorem, which is not difficult. Proof. So I start with this. Integral from a b Fn x minus fx absolute value dx. Of course, this integral is less or equal if instead of this difference I take its supremum. It is less or equal supremum with respect to x. And then if I take supremum, here will be just integral from a b dx. It is b minus a. If we have integral of some function, then of course it's less or equal than supremum multiplied by the length of this segment. And of course, since it converges uniformly, this goes to 0, so the difference goes to 0. This difference goes to 0. In particular, since the difference between two integrals go to 0, Fn uniformly to f implies that you can change limit of integrals with integral of limit. Limit and go to infinity Fn x dx is the same as integral of limit. Which is fx. This is in fact equal fx. So in particular, if sequence converges uniformly, we can change limit and integral. So in some ways complement to Lebesgue's theorem, but Lebesgue's theorem is different. In Lebesgue's theorem, we have only point-wise convergence, but all functions are bounded by integrable function. Here we have stronger convergence, uniform convergence. Now, but we are interested in L2 space, yeah? So, and another consequence of this lemma, of this theorem, so we have even Fn converge to f imply Fn converge to F in L2 space, in L2. No, why? It is clear. Maybe you, I don't know whether you need to write again. If you put here square, it's nothing changed. It is just square, and here would be supremum of square, and it's go to 0. So L2 convergence is just, you see from the proof that you can put here square. In fact, you can put any degree, in degree 4 and so on. In mathematics, people study so-called LP spaces. These are functions such as integral from AB fx in the degree p dx is less than infinity. So we have convergence in any of these LP spaces. So uniform convergence is convergence in any of these LP spaces. Okay, so we study two possible kinds of convergence. In fact, there are three: F and F, F poit-wise, F and F L2, three blocks. So this implies this. This implies this. This does not imply this. This does not imply this. This does not imply this. And this does not imply this because this even does not imply this. Yeah, so this is, yeah, this does not imply this. Yeah. So three types of convergence which are in a rather complicated relation. For this, you are sure that you will get everything. From this, you should be careful. No, you cannot go up. You cannot go up. You cannot go here and here. Yeah. So this is. So we finished the third part of the course, which was different types of convergences. And now I want to prove something about uniform convergence of Fourier series. Uniform convergence of Fourier series. I don't know. I have just idea how it should look. So we start with Fourier series has this form: A0 divided by 2 plus sum n from 1 to infinity an cosinus nx plus en sinus nx. And coefficients, for example, an is given 1 over pi, integral from minus pi to pi, fx cosinus nx dx. The same for sinus. If this, I want that this series would converge uniformly with respect to x. Therefore, I want to get condition when these coefficients are small. So I want that this an go to 0 sufficiently quickly. So I want such Fourier series where these coefficients go to 0 very quickly. Then this guy is bounded by 1. This bounded by 1 uniformly. So we will get uniform convergence. How to get this decreasing? How to get here? I want to integrate by parts in this integral. So we do the form from minus pi to pi. Fx, I put d sinus nx divided by n. Correct? Derivative of sinus, cosinus, yes? Yes. Without minus. Derivative of cosinus minus sinus.
Yes,
Yes.
minus sinus.
Yeah. So now we integrate by parts, and we get 1 over pi, and here is fx sinus nx divided by n minus integral from pi to pi. And here's our 1 over n. 1 over n, what we want, what we badly want. So here is f, now f prime x sinus nx dx from 0, from minus pi to pi. Because of this sinus, this term disappears, is equal to 0. And our first step produced to us 1 over pi n integral from minus pi to pi f prime x sinus nx dx. n. I hope that we approach what I wanted. Now I integrate the second time by part. Yeah. We assume this function is very good. So it would be 1p divided by n. Here sinus now, here now it is derivative, okay, so minus pi, here is f prime x, and here is d cosinus nx divided by n, yeah, n square, and d cosinus disappear this minus, yeah. And we repeat integration by part, what we get, integration by part, so we will get 1p, n square is already good, n square is good, I want to come to the series it converge. 1 over n was not good, but 1 over n square is good, so it's enough 2 times integrate by part. So it would be f prime x cosinus nx from minus pi to pi, and here minus, and here is minus integral from pi to pi f2 prime x cosinus nx dx. So now I want that this would be 0. Maybe it's always 0, but maybe we need to ask that derivative is also periodic. Let us see what this. So f pi cosinus n pi minus f minus pi, and here is cosinus n pi. Now we should consider 2 cases, n to k plus 1. A to k plus 1. It seems it does not work, it would be bad. Because I had the maybe 0, or maybe not. That's so cosinus 2k to pk plus pi cosinus to be cosinus pi. Cosinus pi, it is cosinus pi is minus 1, да? Minus 1. If okay, it's minus 1. A cosinus 2pk minus pi It's also -1. Good. Good. At least for odd, it is good on the condition. We should this is a prime. We should put additional conditions that not only function is periodic, but even derivative give us this. So we ask for this condition. Yeah. Of course, it should be first for in the formulation of theorem, but when we derive, we get conditions in the process of derivation. But what happened? I think if it's if it was just 2k, cosinus 2pk is 1, and cosinus, cosinus minus 2pk is also 1. So it would also disappear. So under this condition, we get this answer. This term will disappear. Under this condition, this term disappears. So we get now the following formula for an. The following formula for an. It is equal 1 over pi n square, and here is integral. From minus pi to pi. I don't think what was the sign. Sign was minus. No, sign does not play any role. The second derivative, cosinus nx dx. No. We can estimate this is just finite number. This integral, you can estimate this integral. So an is less or equal 1 pn squared, and this integral, when we estimate cosinus, it is less or equal than 1. So this is less or equal this integral. Just second derivative dx. So this is number. So all coefficients an, they are majorated in this way. In the same way we get for pn. It's more or less the same plane with sinuses. N square. It will be sinus nx. It is the same majorated by the second derivative. And now we can prove uniform convergence of partial sum of Fourier series to fx. How we do this? It would be if we, or first of all, we prove that this sum Snx minus fx. Let us first prove that it is Cauchy sequence, uniform Cauchy sequence. This is less or equal. Here is sum n from n. For example, if n is larger than m, from m plus 1 to n is an cosinus nx plus bn sinus nx. Yeah. And now we get these estimates to it is less or equal n from m plus 1 to n. And here is some constant, pi multiplied by this integral. Constant, and here is 1 over n squared. Yeah, so it was our aim. To get that it is majorated by this series. But this series converge 1 over n squared. So it go to 0 and m go to infinity. So, and it's uniformly with respect to x. So this estimates go to 0. We can even write here supremum. Supremum x less than 5 minus 1. Yeah. Supremum. Dependence on x disappeared because cosinus is less than equal 1 and sinus is less than equal to 1. So now we know that Snx has uniform limit, so that they converge uniformly. Converge uniformly to the sum of Fourier series. And here we shall use now the theorem which we proved at the beginning, that our function is so good, is differentiable, then of course the sum is equal to fx. But this theorem which was proven. So we found the condition when Fourier, for which Fourier series converge uniformly. Converge uniformly. What was this condition? It was condition that second derivative is periodic. Let us put periodicity for the first derivative, because I suspect that when we work with sinus, the story would be different. We will need periodicity of second derivative for, but we will need, yeah. So let us put, to be sure, even this. Because we did not calculations for sinus, and I suspect that for sinus, it would be on the first step when we shall use periodicity. For cosinus, we use periodicity only for the second derivative, but I suspect that for sinus, we will use it. What is good? The series converge uniformly. Now we can integrate this series. For example, now we can integrate this series. So now the integral fx dx, it is equal the sum it's equal the sum a0 divided by 2 to pi a0 to pi plus integral. It's meaningless to integrate this series. Why? Why it's meaningless to integrate Fourier series from minus pi to pi? Because all these guys will give us 0, yes? If I integrate Fourier series, the only thing which gives me contribution is this term. So, no, I wanted to demonstrate that this theorem has a nice application, because we know that if series converge uniformly, then we can integrate it. But in this case, it's trivial. It's trivial because if we integrate this series, this disappear, would be only this one, but this one is precisely definition of A0 is integral of f. Yeah. So application of this theorem to integration of Fourier series is trivial, it's not useful. In any event, we got the condition when Fourier series converge uniformly. This is also good theorem for exam. So because here you need only integration by parts 2 times. So because this big theorem is very difficult, but this is a good theorem. So theorem that f, or we can write f let f plus C2, so 2 times differentiable, 2 times continuously differentiable, and f prime and f2 be periodic. Then Fourier series converge uniformly. converges uniformly to F. So if function is 2 times differentiable, then Fourier series converge to F uniformly, independently or mixed. Independently or mixed. I think it's enough for today. It's enough for today. And I don't know whether you started to make the second portion of exercises about expansion of functions in Fourier series. It's boring. It's boring because you should calculate integrals, but maybe do at least 1, 2, maybe not all 7 in this file, which I put on my model. There are 7 or 8 exercises, but try to do at least 2, 3, because one of such examples will be on exam. So calculate Fourier coefficients of Fourier series, write Fourier series, and write parseval equality. Yeah. Of course, I shall try to select functions which are easily integrable. For example, step function. Yeah. After this function, yeah. 1 and 0. So on exam, you will not have the problem of calculation of integral, but to have experience is not bad. Okay, so thank you. Thank you.